processor, why not just deploying multiple simpler processors？ 就是与其请一个博士来做这件事，不如请10只猴子来做，就这个意思。就是10个大学刚毕业的来做。So applying this, this is like a design philosophy change. So from single powerful processor to parallel processing. But that requires some big changes too. The first thing is you have to first describe the system, describe your parallelism in your program. 就是在你写程式的时候啊，你就要把平行度写出来，就是谁跟谁可以同时算。So you have to describe explicitly which parts in your program, in your application, can be executed in parallel. Describe your parallelism. So that is something not used to people these days, even today. 就是平行做事情这件事啊，是不是很直觉？就是不是人类可以很直觉、很天然自然可以做得出来的事情。If you can think about it, it's trying to be parallel or increase your level of parallelism is not really human nature. So for you, usually how many things you can do at the same time? Like think at the same time. 你一次可以想几件事情？对吧？一件嘛，2件嘛，对不对？边上课听课，然后边想等下吃什么，差不多就这样子吧。所以不太能做很多同时的时候。In human thinking is a pretty sequential in nature. So you can only focus on 1 or 2 things at the same time, at a time. It's not easy that you focus on 5 different things at the same time. So not easy. So if it's not easy to think things in parallel, then it is not easy to write the parallel program. It's against your nature. So you need training. 你必须要训练啊，你才有方法训练，你才可以去比较，可以接受怎么写这个平行的程式。OK， 这个电影叫《棋王》，我看过，那个谁演的？梁家辉演的。你没看过这个电影啊？就是他一个人跟10个还是8个10个人下盲棋、象棋。哎，没看过这个电影啊？你平常在干嘛？也不看新闻，也不知道八卦，也不看电影，有没有出去玩？平行度高一点好吗？平行度啊 ，increase your parallelism level. Okay. All right. So compared to instruction level parallelism, we talk about instruction level parallelism. So we can expose parallelism at different levels. 就是在不同的层级，展现平行度。有一种平行度的层级叫做 instruction level parallelism. That means we try to expose parallelism at instruction level, meaning we can execute, the CPU can execute multiple instructions at the same time. Okay, let's go instruction. We'll talk about that later in the later chapters. So how we execute multiple instructions at once and hidden from the programmer. That's how we will do that. But it's really hard to program for the performance. We try to do the load balancing and we try to optimize the communication and synchronization. So load balancing is, even though I have several 10 processors, I cannot chop my job. I have a job. I want to use 10 workers to work on this job for me. I have to partition this job into 10 parts. But it's really hard. It's easy to chop into 10 parts, but it's really hard to make sure that 10 parts are equally loaded. That's not easy. 你要切成10份等份，每一个人分到的量都差不多的工作很难，切成10份很难。所以那个叫 load balancing. If you cannot achieve load balancing, that means some worker will work on more heavy job. Some are working on more lightly loaded job. So even though the one with the easy job can finish the job very quick, then everything you still need to wait for the one with the most difficult job to finish. That takes a long time. Okay, load balancing, that would make your performance down degraded. Optimizing communication and synchronization. This is super important. Communication, you have 10 workers working on the same thing. They need to synchronize. They need to talk to each other. Usually, when you try to finish the same job. 当你要完成一件事情的时候，你通常需要沟通协调。那这个通常会是系统效能的瓶颈，也是系统效能的瓶颈。Okay, so that's about multiprocessor. Another important thing about the CPU or the performance called benchmark. Benchmark 就是这种测试程式，就是跑分啊，你有没有手机跑分啊？跑分程式叫 benchmark. So these are the programs used to measure the performance. So it's supposedly typical of actual workload coming from the actual workload. But this benchmark will collect all these programs into the same and put them together and use this to evaluate a computing system. 就是我要评估这台电脑到底效能好不好。我不能只叫它算乘法，我要叫它算加法、减法，去漏资料、写资料，很各式各样，我要测嘛，对不对？你要这个找女婿，你也是要测他各个面相啊，能不能喝酒啊，能不能怎么样啊，就是体力好不好啊之类的，你要测各式各样的面相，所以 benchmark 就做这件事情，它有各式各样的程式去测这个电脑或 CPU 的效能，在做这件事好不好，做那件事好不好。So you need a benchmark that contains various different programs to test different features, from different perspectives to evaluate the performance. And then you take the score from different benchmark programs, combine them together, do an average, and you get a score, 平均. Okay, you get an average score that represents the average performance of this processor, of this CPU. Okay, so there's a company doing this and making money out of it. It's called SPEC. 知道这个 SPEC 啊，这个公司叫 SPEC， 叫 Standard Performance Evaluation Corporation。它就 develop benchmarks for different like CPUs, I/Os, websites, servers. So this one SPEC CPU 2006. It measured the elapsed time to execute a selection of programs and normalize relative to a reference machine. 它把它跑出来的成绩去跟一个参考电脑的效能去做比较，然后算出来一个分数，一比这样 normalize 就是除以一个基准值，它就有个分数了嘛，对不对 ？So you get a reference, you normalize the reference machine and you get a score, and then you take all these reference scores and you do a geometric mean， 就是做一个几何平均。平均有两种，你们知道吗？是有两种，一个叫几何平均，一个叫算术平均。There are two different average. One is called geometric mean, geometric average. One is called arithmetic average. 你们平常怎么算平均啊？就5个东西全部加在一起除以5，这个叫算术平均，你知道吗？那5个东西全部乘在一起然后开5次方根号，5次方，那个叫做几何平均。这有两种平均，哪一种比较好 ？Which one is better? Then you should ask me, what do you mean better? 我每次讲好不好，或是那种什么帅不帅、美不美这种很主观的形容词的时候，不是我了哈，其他人你就要问他。什么？你的美的定义是什么？你的帅的定义是什么？你要先问清楚。通常这个时候就会被扒头。对，人在搞什么？好，哪一个比较好？几何平均还是算术平均比较好 ？Which one is better? depending on what you are measuring. So, 我问你啊，几何平均，我没有黑板啊 ，I don't have the board， 在那边啊。几何平均就是我有分数嘛，10分、20分，全部乘在一起，然后开几个分数就开几次方的根号。我问你，假如你是 ，if you are trying to optimize or increase the let's say I have 10 score here. I have 10, like 10, 20, 1.2, 11, different scores and multiply them together. And then I do the square, not the square, 这个开根号，开几次方哈。我问你啊 ，if you are the system optimizer, which program out of the 10, you are going to optimize it? 你要只挑一个程式 optimize 的话，你会选哪一个？让你的分数最高？你会选哪一个？分就是它有的跑10秒，有的跑20，有的跑3，有的跑1.5，有的跑6，有的跑全部乘在一起，然后开那个次方。你会选哪一个 program 去优化它，让你最后分数是出来是最好的？我假设最低好吗？那个时间最小，你会选哪一个？你会选那个数字最大那一个吗？就是有一个跑100秒，有一个跑10秒。那个100其实是相对哈，那个 so the score is a relative score， 就是跟你的基准 CPU 比起来。So there's a one that takes 100, there's 100 seconds, there's one takes 10, there's one take 1.5. Which one are you going to optimize it? If you can only pick one. 你应该数字最大那个吗？假如我是用几何平均的话，假如我是用算术平均的话，你会挑数字最大那一个，因为你这么大，对不对？你只要下来一点点，其他都很小，然后你整个 overall 加起来就会更小，就会减的比较多。假如是几何平均呢，你会挑数字最大那一个吗？不会，不一定。那你会挑哪一个？我会挑那个我可以进步幅度最大的那一个。我不一定是数字 overall 最大，我是进步幅度最大的那一个。我可以，假如有一个100秒，我可以把它变成95，哇，我减5秒了，很厉害。有另外一个跑1.5秒，我可以把它从1.5降到0.5秒而已。你觉得，假如是几何平均，我会选哪一个？我会选那个1.5秒，因为它等比例乘到所有东西上面去，你那个加速是最多的。Making sense to you? So depending on what you're looking at, you will choose different benchmark to optimize. And that's what these CPU companies are doing. They use geometric mean and then they choose the right benchmark they want to optimize. And the one that they choose is the one that you can improve the most in terms of the percentage for that specific benchmark. Okay, is that making sense? All right, so this is just the spec speed for Intel Xeon E5 processors for your reference. 这个参考啊，长得就像这样子。So it looks like this. For different benchmark, you have different scores. And then in the end, you do the geometric mean. 这是几何平均啊，几何平均。Okay. Right, there are other ways of evaluating performance. Again, when people are talking about, when you are discussing performance with your friend or your colleagues, make sure you know the definition of the performance. So there are different ways of evaluating the performance. This is a good example. In this case, what we are looking at is called overall server-side Java operation per watt. 这个通常叫做power efficiency or energy efficiency. What does that mean? That means Whenever I burn a watt or a joule, 一焦耳或是一瓦的 power. Whenever I burn this much energy, how much work can I finish? 就是我吃一碗饭，我可以跑多远的 ？OK， 然后在我倒下之前，对，我不是在比说我从这里跑100公尺谁跑最快，我是比吃完一碗饭谁可以跑最远，就是在消耗掉1焦耳的能量的时候，我们大家都消耗1焦耳，谁走最远？不一定是跑最快那一个，对，不一定是跑最快那一个。So this is to evaluate every unit energy you burned, you consume, how much work you can finish. So this is called power benchmark. So this is a good example of different ways of looking at performance. Okay, so if you look at the power, average power versus the percentage of the loading, 就是你的 CPU 是不是满载比例和 power 哈 then you can find out that it's not linear, 它不是线性的。So if you're 100%, that's 340 watt. If you're 90, that's 312, and all the way down to 10%. Even though if your CPU is only 10% loaded, 你有10%在跑10%, 90%都在 idle, you still consume 100 watt, 115 watt. But if you turn it down to 0, if you don't, all the processor is idle. The processor is like completely idle, doing nothing. You still consume 48 watt. 你还是烧48瓦，什么事都没做，你在那边变成那个电热器。So, in this case, it's not linear. Then you have a sweet spot of working, and you have a good strategy of managing your processor. For example, if this is the case, I would probably boost my performance and finish the job as quick as possible, and then turn my computer down. 假如是这个样子的话，我通常会想办法超频，把我东西赶快算完，然后把电脑关掉。其实是最省的，因为我什么都不算，我放在那边0%，它也是给我烧48瓦，我不如把它关了，对不对？所以有的时候你看这种非线性的特性的时候，你的策略就要有比较可以优化，不是1分钱1分货，1分钱可能有时候是5分货这样。All right, pitfall, Amdahl's law, 安朵定律哈。So this is very important law, and you can pretty much use it in your daily life. So this is to improving an aspect of a computer and expect a proportion of the improvement in overall performance. 很饶舌，不知道他在讲什么。他这个公式的意思就是告诉你，你常做的事情，你那个说你要优化你生命中的事情的话，你要优化那个你常做的那一件事，你最常做的那件事，你要做最常做的那件事。So 看起来不像这公式不是讲这件事吗？我等一下再翻译给你听。So this is to discuss, tell you that the total time of improvement is, okay. Let's say for an application, there are 2 parts. 一个应用执行10秒，它会有2种部分，一种是你可以优化的部分，一种是你不能优化的部分。So there are 2 parts. One is the time. If the application takes 10 seconds, there are several seconds of the program that you can improve it. The other parts you cannot. So there are 2 different parts. So you want to calculate the time after you apply your improvement or optimization. That the calculation will be how much time you can improve divided by how much you can improve it. 对不对？这个5秒。这5秒钟，你可以让它变，你可以把它进步3倍，就除以3，5秒就变5/3秒。And plus the other parts that you cannot improve it. 这个是你不能，另外5秒也不能。So use this equation, and after that you add them together. That's the total improved time. That makes sense, right? 这可以了啊，简单。好 ，example. We try to multiply the accounts for 80 second out of 100 second. How much improvement in multiplication performance to get 5x overall? 就是我100秒里面有80秒在做乘法 ，so out of 100 seconds, I spent 80 seconds to do multiplication. How much faster I should make the multiplication in order to achieve total 5 times 5x faster， 就是我要让整个系统快5倍，那我那个乘法要让它快几倍才能做到这件事情？答案是你做不到。So if you apply the Amdahl's law, the total time that you need to achieve after 5x overall improvement is to reduce from 100 seconds to 20。你要从100变20，你才是加速5倍嘛。你的目标是20。And out of this 100, 80 of them is multiplication, 乘法. And how much faster you need to make your multiplication? I don't know. And plus the remaining part is the part that you cannot improve it. All right. So if you want to solve this, n need to be infinite, n 要无限大。所以做不太大嘛，做不太大。So the conclusion, the takeaway is try to optimize the thing that you are doing frequently， 就是你常做的那一件事情，就是这个地方占越大的哈，你要先去优化那个东西。So try to optimize the things that you are doing frequently， OK？ 所以常常见到的人就要选比较帅的，不常见到就不要。Okay, so the other low power fallacy is the list that we just saw, this one. Even though I'm idling, I'm still burning 48 watts. So that's something really serious. So at 100%, that's 250 watt, 50, that's 170 watt, 10%, that's still 121 watts. These numbers are slightly different. From processor to processor， 就不同 processor 不太一样，但是趋势都差不多。So for the Google data center, most of the data center processors they are operating at 10 to 50%， 只有10到50%的 loading。So only less than 1% at 100% of time. So what we are trying to do is either we design a processor that make power proportional to load。要么我们就设计一个处理器，它的效能跟它的耗能量是成正比，这是成线性的，要不然我就是 race to halt， 我就是赶快跑完，然后把它关掉。Okay, so that's if you look at that number, it can help you to do the right strategy. MIPS as performance metrics. What is MIPS? MIPS is millions of instructions per second， 每秒跑的指令数量100万，有几个百万，每秒跑几百万个指令，这是一个评估的参数，叫 MIPS， millions of instructions per second. So if a processor that has higher MIPS， 一秒跑的指令数比较高 ，higher million instruction per second, that means this processor has better performance. Is that a correct statement? 是吧？每秒的跑的指令数越多的，它的效能就越好。我每秒可以执行500万个指令，和另外一台机器每秒可以执行800万个指令，哪一个机器效能比较好？效能就是算的速度会比较快。There's a machine with 8 MIPS and the other machine with 5 MIPS. 5 million instructions per second. Which one has better performance? Which one can finish the same program, in a shorter time? The one with the 8 MIPS, 8 million per instruction per second, or 5? The answer is, I don't know. 我问你啊，两个人比，就是， 两个人跑操场1圈，有一个人呢，他每秒可以跑3步，有一个人呢，每秒可以跑2步，请问谁会赢？不知道嘛？看步伐大小嘛，对不对？ So exactly the same thing here. This one, by only looking at the MIPS, you don't know. You don't actually know. You don't know what instruction you executed. Doesn't matter how many, because I don't know which instruction. 说不定你做了一堆就是虚功，对不对？你跑800个指令，没有跑800万个指令，可其中有一堆都是就是不知道在干嘛的东西搬来搬去，很无聊的。没有什么意义的事，没有效的运算。So MIPS by itself is not the good, or it's a reference factor, but you cannot just look at this one only. Okay, you have to look at others. Okay. Oh, 最后一页。So the concluding remark is, we try to optimize the cost per performance. It's improving because the technology development, and we also talk about hierarchical layers of abstraction in both hardware and software, and we try to we'll talk about instruction set architecture, and that's the hardware software interface. And the performance in this lecture, in this class, only in this class, 在我们这课里面，只有在这个课里面啊 we use execution time to represent the performance. Okay, so power is a limiting factor. You cannot just use as much power as you want. All right. Any questions? Nice. All right, we'll still have time. Let's move on to chapter 2. So that will be chapter 1. Any questions? 有什么问题吗？ Chapter 1. All right, so for chapter 1, we use 3 weeks to finish chapter 1. It's so slow, but I try to be that slow on purpose in order for all the students with different backgrounds to catch up. So if you are still lagging behind, try to catch up as quick as you can. 就是我是故意很慢啊，前几第一章尤其是让大家赶快追上来。你假如还没追上啊，那就要考虑一下是不是要去那个退选了，或者是好像几个小时而已嘛，2个小时的那个攻读。Okay, so all right, in chapter 2, we start talking about instructions. So instructions are the language for computer. You tell the computer or tell the CPU what to do. So usually we call instruction set, 就是我们叫它指令集啊，集合。Instruction set, that's a set of instruction that you can use that set of instruction to tell the computer what to do. It's like the calculator, 就像计算机，你可以叫它算加法、减法、乘法、除法、开根号，所以那些就叫指令。你要这个资料从这边搬到那边，然后做个加法，然后往左 shift 2格，然后再乘以3，然后再放回去记忆体，一步一步。So these are the steps that you want to do, and you want to tell your computer to do these steps or operations by sending the corresponding instructions. 给它适当的指令。And different instruction, different computers will use different instruction set, but most of them, a lot of them, have many aspects in common. 就指令集不太一样，有很多指令集。你们有听过哪些指令集？像 ARM 对不对 ？ARM is an instruction set. ARM itself actually has several different instruction sets. 什么 ARM 64啊 ，ARM 32啊，什么那个叫什么东西啊？它有各式各样不同的指令集。ARM 本身就有 ，ARM has different instruction set. What else have you heard? x86 x86 啊，对不对？还有什么 MIPS, RISC-V. So these are all instruction sets. Spark, PowerPC, right? These are different instruction sets. They are used by different computers, but a lot of the aspects are in common. 很多地方是很像。 Early computers are very simple instruction set that will simplify the implementation. Any modern computers also have simple instruction set， 就是很早以前的电脑呢的指令集很简单，就加、减、除啊，那现在的指令，现在的电脑指令集也是很简单的，所以我们叫它RISC instruction set， 叫做 Reduced Instruction Set Architecture. So RISC is called reduced. 这个超难写的。Instruction set computer. Okay, reduce instruction set computer. So RISC-V instruction set is this called RISC reduced instruction set computer.RISC-V that means generation， 这个是罗马数字的第5代的意思啊，第5代 V 是5嘛，对不对？罗马数字的5，所以 usually we call RISC-V, not RISC-V. It's RISC-V instruction set. This is an instruction set coming out of Berkeley, and we will use this instruction set as an example throughout the book. 我们这一本课本会用这个当做例子而已。那developed at UC Berkeley as an open ISA instruction set architecture, and now managed by the RISC-V Foundation, and typical of many modern ISA. And you can see the instruction set reference data from the book. 你可以去参考啊哈。那similar instruction set architecture ISA have a large share of embedded core market, and including applications in consumer electronics, network storage, camera, printers. First of all, in this class, I will not ask you to memorize the instructions. 我就是这门课不会叫你去记指令长怎么样，不会，因为我也背不起来，所以我背不起来的东西，我会叫你去背。那不用背，那就是指令长的样子，你拿个字典翻一翻就好了。So you don't have to memorize the instruction syntax, exact syntax， 就那句型什么东西你不用记。But you have to know the fundamental. You have to know the fundamental usage or fundamental format， 就是基本的格式你要知道。So what's the fundamental format? This is the fundamental format. So for RISC instruction, for arithmetic operations， 就是这种算术运算、数值计算的时候。For example, addition, subtraction, or division, multiplication， 加减乘除这种东西 ，you have 3 operands， 你有3个运算的单元，2个是 2 are sources and 1 is destination. So, for example, if I write this add A, B, C, that means I want to add B and C, and the results I want to put into A. 像这样就是 B 加 C。然后放到 A. So that's the fundamental format you need to know. This one. OK， 像这个你要知道啊，这个是比较基本的格式。那实际上在 RISC-V 里面的加法不是长这样，它不是写 ADDI， 它写一个奇怪的东西 ，ADD 什么什么 ，ADDAI 啊，或 ADDD 啊，什么奇奇怪怪的 A 啊，它都是加法。那你不需要去记那个东西。然后后面的这个呢 ，A B C 呢 ，so add is the operation, so it can be represented in different instruction sets. And A, B, C are usually registers. 这个通常是暂存器啊，就是 register 0, register 1, register 2. They are registers inside the processor. So here we use A, B, C. You don't have to memorize all those names, but you have to know this is the basic format. Okay. So all these arithmetic operations have this form. So design principle 1 is we try to do simple design. So simplicity favors regularity. 你东西越简单，你就可以比较规律的、规则的 去设计你的东西。很好的例子叫做乐高嘛，对不对？乐高东西都很简单的，但是你就可以很规则、很规律的去拼出很大的一个恐龙或者什么很复杂的东西。So regularity makes implementation simpler, and simplicity enables high performance at lower cost. Okay, so this is called arithmetic operation. Let's look at one example. C code. When you write a C code or Python code, whatever code, high-level code, you want to add G and H, you want to add I and a J, and you want to take this one and minus that one. So if you write it into RISC-V code, it looks like this. You add G and H, and you put into temporary T0. You add I and J, you put into temporary T1. And then you add T0 and the T1. And you put it into F. So you should do, 你应该是用减吧？这个 this should be sub， 这个不是加，这个应该是减吧？ This should be sub, S-U-B, okay, sub T0 minus sub T1, and you put the result into F, and that's your program. 这个怎么会犯这种错误啊？这个投影片是这个书商做的哈，所以很烂，没有好好检查。All right, so register operands. Usually for arithmetic instructions, we use register operands. 我看不到时间了，所以下课就让我知道一下。38块。好，我们讲完这两个页段。So RISC-V has a 32 64-bit register file. 这个需要黑板画图。All right, let me go through it. So I will try to draw the figure again next time. So uses for frequently accessed data and 64-bit data is called double word. So inside RISC-V, there are 32 registers, 有32个暂存器 and each one has 64 bits. 每一个是64 bit 长，然后有32组，对，32组这个东西。So these are 32 general purpose registers, and their names are X0 to X31. 这是它名称啊，从 X0 到 X31， 就是这是它的名称。Usually we call 32-bit data a word. 通常我们说一个 word 是32 bit 嘛。And 64 bits we usually call a double word, 就是两个 word, double word. And design principle 2, smaller is faster. Okay, probably you don't understand that right now, but the idea is when processors are running, it needs data. 就是处理器在跑的时候，它需要资料。所以这个 where are the data? Where are the data for the processor to run? If I want to add A plus B, I need to have A and a B first, right? So where are they? A 和 B 它们在哪里呢？ They're in memory, right? In your hard disk, 你的硬碟里面。So when you turn on the computer, it's in the disk. So CPU processor start loading this A and B in, loading from your disk into the DRAM, and then loading from the DRAM to the processor. And where do you store this A and B when they are in the processor? 当 A、B 进到 processor 里面的时候，存在哪里呢？ They are in registers， 就是那32组64 bit 长的那个 register， 32组存在其中里面。But why do you need so many registers in the processor? Because the data when you store in the memory or in the disk, it will take a long time to get it. The disk and the memory DRAM is really slow compared to processor. 就是记忆体跟你的硬碟啊，或者你 SSD 固态硬碟啊 ，USB， 它跟 CPU 比起来是很慢的东西，非常慢的东西。So when you need the data, you have to load it from the memory. So if you know that you want to work on this data, it's better that you put these data, important data, in the memory that is fast. So this register 32 register, these registers are the fast memory. 这些 registers 是快的 memory， 所以你要把它放在快的 memory 里面。啊，这个需要图，没有图在没办法解释，你们也不知道我到底要讲什么，好像在讲了一些字，好像很有意义，可是其实听不太懂到底是代表什么意思。我们下次再来画图。All right, so we mentioned that there are 32 general purpose register X10, X0 to X31. So X0 to X31 here, they are used for different purposes. 它们有一些预设的一些目的使用的方法，这个我们下次再讲。有一些叫 return address, some are used to represent zeros, some are used to do the return address, stack pointer, global pointer, third pointer, etc. Okay? All right, I think that's it for today. We will continue next week. So again, starting next week, we should start using our new schedule. That means 你记得我们的 new schedule. So starting from next week, we'll start using our new schedule. So our new schedule is, instead of having a 1 hour, 50-minute session on Thursday, we will focus on Tuesday. We'll start 10 minutes earlier, finish 10 minutes later, and we'll skip the break. Okay? So if we can be on track of our lecture, then we will skip the Thursday lecture. Okay? 就是假如我们这样子讲得完的话，礼拜二讲得完，我们星期四就不来了啊，这样大家就都很开心。Okay? All right. Any questions? 有什么问题？ Alright, now see you next Tuesday. Okay, 有问题？
问一下，就是